Right, let's get started. Before we get started, can I get a show of hands here? How many of you are familiar with Postgres logical replication? Have worked with logical replication before? Okay, a few. Can I get another show of hands? How many of you work on platform or infrastructure related stuff and not product stuff at your companies? Okay, 3 or 4 people. So imagine you're on a platform team and you're tasked with the critical mission of ensuring data consistency and reliability between Postgres and other distributed systems. How would you approach this problem? I look forward to sharing my perspective on this. Good morning, everyone, and welcome to this session on building reliable and scalable data replication pipelines from Postgres on Kubernetes. This presentation is not a deep dive or a technical deep dive into the internals of logical replication itself, but rather I will share my and my team's experiences on building such a reliable data replication platform at Datadog, the company I work at. So a bit about myself. My name is Sanketh Balakrishna, and I'm from Bangalore, India, and I currently live in Lowell, Massachusetts. And I'm an engineering manager at Datadog, where I manage MARS, which stands for Managed Replication and Search, our data replication and search platforms. In my spare time, I enjoy playing racket sports like badminton, table tennis, sometimes tennis and squash as well, and of course, pickleball, which I know is pretty popular here in Florida. I also enjoy traveling and the outdoors. Last year, my wife and I, we hiked the Half Dome in Yosemite, which I know is one of the more challenging hikes here in the US. So before I start my agenda, let me give a brief introduction to Datadog, to those of you that don't know. This is not a sales pitch, but I will reference Datadog a couple of times later on in my talk, so it's important to get some context on what Datadog is, right? So Datadog is the observability, monitoring, and security platform, which collects a lot of your data from various different sources like logs, traces, and metrics, and provides a unified view of your data, along with a bunch of platform services for you to solve your customer issues. But the key takeaway from this is that massive scale, lots of services and products, and lots of use cases we help our customers with. So at Datadog, as we saw, we deal with large amounts of data, right? So in order for us to, for product teams to focus on their customers, we have strong platform teams to enable those faster iterations for products. And managed core database engines are also integral to a reliable platform. And managed core database engines are also part of platform at Datadog. And we also have a strong affinity to use and contribute to open source products at Datadog and at platform at Datadog. So why do I mention all this, and how is this related to Postgres, right? So Postgres has been the most popular database now for at least 2 years in a row, but many more years, we all know. I'm just quoting the Stack Overflow developer survey here. It's a #1 database, and it has a lot of history at Datadog as well. Postgres, we kind of going back a couple of years at Datadog, right? When we were looking to work on the next set of problems, we made a number of observations. So the first observation here is that lots of teams already had data in Postgres. So Postgres is just easy, it's highly reliable, and it's most important of all, open source with a strong community support. So teams were just using it for years. So Datadog is around 15 years old now, and Postgres also has a long history at Datadog. So they were used to using Postgres, and they were used to administering Postgres. So it was clear that it wasn't going away anywhere, anytime soon. We were also building, upgrading, and investing in our Postgres on Kubernetes platform. So just to give a bit of context on this, a Postgres on Kubernetes platform can look something like this. So you have a leader pool and a replica pool, and the leader pool can have a leader and standby nodes, and the replica pool can have one or more read replicas. And you have streaming replication here from your leader pool to the replica pool and from leader to standby as well. And replication in this case can be either synchronous or asynchronous. And you have your application on the left here, which can connect to the database either directly or through a proxy layer in between. Questions at the end? Okay. Thank you. So the application here can connect to the database directly or through a proxy. And all of these database components are hosted on Kubernetes, and hence Postgres on Kubernetes, right? And there's the orchestration system and some other components which will need to exist here as well, which is missing from this picture. But overall, there's a lot of flexibility with this architecture. So with the growth of our products, we wanted to bring some structure into our managed Postgres on Kubernetes fleet. We also wanted to upgrade some of our legacy old databases and break up some of our large monolithic databases that we had into smaller tenants to improve reliability. We also noticed that search was becoming increasingly important at Datadog. So what do I mean by this, right? So if you go to the Datadog app and you look at some services, you'll quickly notice that there's lots of search bars and lots of facets which make it easy for you to find your data. So let's take some examples. The first one is the monitors page, where you can view and define all of your monitors. For context, monitors are used for the proactive detection and the real-time response to all of your performance issues and outages. So you can just define a monitor and based on a certain metric and a certain threshold, and if the metric reaches a threshold, you get alerted before the issue happens. So the important key point to see here on this is that there is a search bar to the top and some facets to the left. Here's another example, the dashboards page, which provides real-time insights into the performance and health of your systems. And dashboards consist of a bunch of widgets, and each widget tracks a certain metrics. And overall, you can see the health of your entire system on a single dashboard. But here you can see the search bar here and some filters to the left here as well. Another example is our notebooks page, which are collaborative text editors you can use to visualize graphs and build documents. Again, search bar to the top and some facets here right below it as well. So you get the point here. So search was becoming increasingly important, and lots of data for these products were stored in data stores like Postgres already, right? And the question which we faced a couple of years ago was, how do we enable fast faceted search and full text search when data is already in Postgres, and how do we scale that to the number of users and customers that Datadog supports? So there are some advanced search capabilities that Postgres provides, like TS vector for full text search, or extensions like PG vector for nearest neighbor or similarity searches. We already had a few different PG vector talks here at the Postgres Conference as well. So there are some limitations which you get. Like if data sets grow to millions of records, search engines tend to outperform Postgres, as data grows and as databases scale. There are limitations like row size limits, increased complexity, and horizontal scaling limits, which Postgres will run into eventually. Search queries can become complex, and interfaces and abstractions are not easy to build. The next observation we made was that the same data was needed by multiple teams. So multiple different teams at Datadog wanted access to similar kinds of data, but with slightly different flavors. So some teams wanted data with strict access control. Some teams wanted some data masking for fields like sensitive fields. And some other teams wanted some filtering on that data and single message transformations on that data. So building tightly coupled integrations on top of Postgres became quite challenging. So based on these observations, we came up with a set of requirements. And this is not a comprehensive set of requirements, of course, but I listed the three main ones. Firstly, we needed to replicate data from Postgres. So we were clear from day one that we did not want to build all these search and analytics systems on top of Postgres, but rather we needed a way to replicate and migrate data out of Postgres. And the second requirement was that we wanted to build reliable systems that could scale. So using a trigger and a change log table that we could poll, I know we used to do that like 10 years ago, I guess, was an option for us, but it wasn't a real option that we wanted to consider. And the third requirement here is that the target systems could vary. We wanted to start with the problem of search, full text and fast faceted search, but we also wanted to make this a generic platform that could scale. So to fulfill our requirements, I think it was quite clear from day one that we wanted to use logical replication from Postgres. So extending our Postgres on Kubernetes architecture, now we have a publisher and a subscriber, and some of the logical replication components here, like the wall sender, which reads the shared write-ahead logs and uses the logical decoding plugin to decode the wall files and sends the change events to the apply worker on the subscriber. And on the subscriber side, you have the apply worker applying those changes on the tables and sending acknowledgements back, thereby advancing the replication slot and allowing the older write-ahead logs to be archived. So this is all standard Postgres logical replication, nothing new, nothing but that we built, but it does provide some benefits for us. The first one is fine-grained control over the data. So remember I mentioned that some teams wanted some data and some teams did not want some columns in some data. So it provides fine-grained control over what schemas, tables, and even columns we replicate from this. It allows for flexibility, right? So we can replicate between Postgres of different versions or Postgres instances between different platforms. It also allows for transactional consistency, the order in which the changes are applied on the subscriber, and the order is the same order that the changes happen on the publisher in this particular architecture. And you also get real-time updates. Updates are not practically real-time. It depends on a lot of factors. But of course, the expectation is that the change events, the replication here is near real-time. So once we decided to go ahead with logical replication, and if you are thinking about using logical replication, there's two main approaches, broad approaches to replication you can take. So the first one is synchronous replication, where the primary and the secondary systems are fully synchronous. Here, the data is strongly consistent. You typically have lesser components to manage. But on the other hand, there are some trade-offs and drawbacks here. It's less flexible typically and more prone to flakiness. And here, synchronous doesn't mean leader to standby synchronous or leader to read replica synchronous, but synchronous between the primary and the secondary systems. Postgres to Postgres replication is a typical example of this. And another example is pgsync, which is a middleware for replicating data between Postgres and Elasticsearch. The other way to replicate data is, of course, asynchronous replication. And here, the subscriber is much closer to Postgres. And you have another system which will need to apply the changes on the target. This system is typically more scalable and more reliable. But on the other hand, you have a lot of moving pieces you need to manage. And data is less consistent because now you have two pieces you need to manage rather than just one. An example for this is Debezium-based replication. So Debezium is an open source platform for distributed change data capture. And Debezium is built on top of Kafka Connect, and it provides a lot of connectors out of the box. And extending on our previous Postgres to Postgres publisher-subscriber model, now the subscriber here is Debezium. So it reads the change events and sends those acknowledgements back, but because it is built on top of Kafka Connect, it sends those change events to Kafka, and you typically have a sync connector connecting to various different databases and sending the data over there. So this checked off all of our requirements. Now we had an ability to replicate data from Postgres. We were betting on this being scalable and reliable, and target systems can now vary, and the target can pretty much be anything. So as we have built the platform over the years, there were some challenges that we faced. There are many to list, but I've listed the top 4 challenges which we have faced, and I'm going to talk about these 4 challenges. provisioning, metrics and traces, schema-related challenges, and customization. So the first problem I'll talk about is provisioning. So building a reliable platform-level data replication pipelines that are used by many different teams means that there are a lot of moving components to manage. So take Postgres operations, for example, right? When you have to enable logical replication on Postgres, you have to set the wall level to logical. You have to create certain users, grant permissions and privileges to those users. You also have to create the replication objects, like the publication and the replication slot. And you also have to create the resources and ensure that the replication slots are fully consumed and are not inactive in production. So initially, all of these were manual operations that we did. For the first few users, we were a pretty small team. And we were fully, working with our internal users and getting this set up manually in all production regions. A related issue here is repetitive user asks. So users typically have the same kind of requests. So we have multiple data centers and regional isolation. So we needed to kind of provision all of this wherever our customers were. So this is actually a typical conversation, not a real conversation, of course, but where a user asks in our initial days, can we get replication set up in these 10 different regions? And we're like, okay, sure, give me a month so I can run all these 50 steps everywhere. We luckily realized this problem early on, and we solved this problem by building automation. So if you are building a platform solution of any kind, generally focus on this right after the first couple of users. Especially when there are lots of moving pieces like this, automation is generally hard to build, and provisioning is hard to automate in general. But if you start small with incremental updates and with the right set of constraints, you'll save a ton of developer time to later on to focus on bigger problems. The second problem I want to talk about is metrics and traces. So when you have a multi-component architecture like you do here, like Postgres, Debezium, Kafka, Sync, and Target, each component may have its own way of emitting metrics. So Postgres, for example, does not have a native way to emit metrics. It doesn't have a metrics endpoint. But Debezium and Kafka are Java-based and have integrations it emits metrics to JMX, and Sync and Target can have its own way of emitting metrics, right? So having a unified metrics view was generally useful for us to think about. Users also care about end-to-end latency. So when we used to talk to many different product teams, one of the first questions they asked is, what's the end-to-end latency of this data replication system? Right? So end-to-end latency is generally good to think about if you're building a logical replication pipeline. And the third one here was tracing a request. So what happens if your request fails? What happens if a certain request takes longer? So generally, it's useful to have a trace of a request through the pipeline, just because there are so many components involved. So let's go one by one. All this. The first one is the unified view for this metrics. And the easy answer here we had already was Datadog, right? So Datadog, some metrics which you see here are Datadog built-in metrics for pods and containers. Some are JMX metrics and some are custom metrics. So Datadog provides this dashboard feature where you can, that I spoke about earlier, where you can view all of these metrics in one place. So at the top, you see some Debezium metrics there and some Sync metrics, some Kafka metrics, and also some replication lag metrics. So we got this one for free, basically. The next one is measuring latency. So end-to-end latency is not really trivial to measure. It's it's a bit complicated because you have like many different systems. And one naive way to measure latency, is generate a timestamp at the source, generate a timestamp at the target, get the difference, and now you have the latency. That's actually one of the first ways that we did measure latency. And it works fairly well, I would say. But it's a complicated problem when you want to get it like down to the microseconds, right. So another way is that you can use or update an external data store with the latency of your system and allow the external data store to measure your platform level health and latencies. So the next problem that we were looking at was tracing a request and through distributed tracing. So tracing is a way to track and observe requests as they flow through the pipeline. And Debezium here actually has an active tracing spans single message transform. And Debezium offers to create traces if it does not exist. So you have a parent trace ID, and each component creates a span and attaches the parent trace ID there. And then you can use Datadog, for example, to view those traces. This is active tracing span. Debezium's single message transform wasn't fully working. So Jean from our team actually made a contribution to kind of fix that and make it fully working for a logical replication pipeline. So this is how traces can be visualized. As you can see here, you have the flame graph or the waterfall view or many other different views here. And here you can see the trace and individual spans. You see the application took 20 milliseconds, the Postgres write around 500, 600 milliseconds, Debezium read around 400, and sync with 400 milliseconds. This is actually an outlier, not our actual times here, just an outlier that I took because the distribution is more here. So now I want to talk about schema issues, right? So there are plenty of schema issues to talk about, but I've chosen two here, and the two main ones. The first one is that DDLs are not supported through replication, and this is a pretty big drawback for us because we have a lot of product teams, a lot of databases, and they make a lot of changes regularly to those databases. So how do we kind of detect all of the DDL changes that they make, and how do we kind of replicate over so that the target system and the pipeline itself does not fail? And the second one here is that the relational structure is broken after data kind of leaves Postgres. And this is a more important problem to discuss, in my opinion, because you see the example here. You have three tables, and table 2 has foreign key relationship with table 1 and table 3. And you can have some other constraints as well, like primary keys, not null constraints, etc. As soon as you replicate that over to Debezium, now you lose all of those relationships because Debezium just understands, okay, insert, update, delete, row, and then the data itself, right? So you lose all of the relationships, and now you have to kind of figure out what row, what order you have to apply the changes in. So we have been able to find some solutions to these issues. So the first one I'll talk about is using some kind of a schema enforcer, like schema registry. And schema registry is just a repository of schemas. It's a pretty lightweight application, and it's open source as well. And how this works is that every message that Debezium sends to Kafka, it checks with the schema registry. Does this, is the schema compatible? And if that message, if the schema does not exist, then it creates one. If the schema already exists, then it checks whether that message is compatible with the earlier schema or not. The same thing with the sync. It checks with the schema registry whether the message is compatible before sending that over to the target. So this has actually worked quite well for us. We encountered many different issues and uncovered many issues using the schema registry. So it's a pretty important component to have if you're using or thinking about using or building a logical replication pipeline. So the second one is enforcing validations, and this is a platform level challenge that we solved. So a lot of teams, as I mentioned, make migrations and changes to their databases constantly. Some of those migrations break our replication pipelines. Like for example, altering table renaming column or adding certain columns or deleting or dropping columns is not supported when it's not done in a certain order, right? So we had this simple flow where the user makes changes, we have the CI/CD job, and we kind of check if if logical replication is enabled on Postgres, on their Postgres database, and if it is, we kind of have a list of breaking changes that we have identified. If it's a breaking change, then the user has to go back and make those changes in order. If not, then you kind of apply that migration onto the database. So this is kind of step one. There's lots more to come here in this space. We want to make it fully automated, but this has till now worked well for us. The last problem I'll talk about is customization, and this is more of a platform challenge than a replication challenge. So as your platform grows, each team will want a different flavor of your platform. So how do you handle multiple requests from teams when you're kind of, have a lot of requests and a lot of features to build for different product teams. So the first solution here is to generalize your platform, right? So you don't want to build something which is in the product domain, or you don't want to get into something that affects a single product, but you want to generalize your platform so that you can scale. The second one, and having said that, is that white cloud support is unavoidable, right? So the true value of a platform team is realized only when they kind of create value for product teams. And there's been lots of teams that we have worked with and provided white cloud support, and it's generally unavoidable. And think about if features are right fit for your platform. So there are certain features which clearly are in the product domain, and there are certain features which belong in your platform domain. So we have regular planning sessions for, for thinking if this belongs in the platform. Now, switching gears a little bit, I want to talk about real-world use case we have solved. So this is one of our product teams had their architecture, and this was before a couple of years, and they had their data stored in this monolithic database with, there were lots of tables, but let's take an example that they had 2 tables, and then you have the application reading from those tables, and then you have the UI and the end user, which are Datadog customers, reading from the UI, right? So this team, they were, kind of doing things pretty inefficiently. So their application were joining like lots of data, like millions of rows at query time. And that was kind of leading to this really high latency, sometimes 30-second plus latencies for Datadog customers, which was completely unacceptable. So we identified a few different problems and used data replication because we didn't want to go and re-architect the entire monolithic database because it was used by many different teams at Datadog. So we kind of enabled logical replication and replicated all of the information that is needed for the search onto a search engine. And we also denormalized the data. So we replicated both these different tables into a single index. And we added a purge job at the top there because there was a lot of data in Postgres which was not needed, and the teams were clear that they needed to purge data after a certain time period. So now we saw some really nice results and impact here with this. So we saw a 41% average decrease in P90 load time, but that was not the interesting part. The interesting part here is that some customers, Datadog customers, some large Datadog customers, saw a drop in latency of up to 95% plus. So the latency drops were sometimes from 27 to 30 seconds to less than a second. Right? So that's a big impact and change right there. Right? So with this, let me also talk about something that did not work. Right? So because we want to get the full picture of what works and what doesn't work, right? So we were working with another platform team, which had an application which sends lots of updates to Postgres. And initially, their architecture was simple. They had a single table, which they were sending all their inserts, updates, deletes to. It worked quite well in our testing phase and with our early adopters, which are Datadog customers. But once they went into production, we started seeing lots of updates sent in by customers and lots of spiky updates. And this generally became quite painful for us because of the shared write-ahead logs that Postgres has and the way that logical replication works. So Debezium is pretty much forced to be single-threaded there. And that was quite a big bottleneck for us. So it was quite painful to deal with this, lots of pages that we got, and we had to eventually roll this back. And since then, we have kind of benchmarked our limits with Debezium and all of our connectors. We had quite a few different action items from this. So we know the limits of Debezium and the limits of what's available, and we're also trying to build and improve our system internally. We have our own Debezium fork that we work off of. So some of the key takeaways here, the first one is architecture is quite important. As we saw those two examples, one of it was like well re-architected, and it was not architected well before. And the second one was not architected well from the start as well. So architecture is pretty important here. Second one, shared write-ahead log is a bottleneck which we kind of live with. It would be really cool to see the Postgres community go in and build some parallelism, which change data capture. I know that it's easier said than done, but that would be a pretty cool feature to have. And third one is building generalizable solutions that can scale rather than focusing. I mean, of course, we need to focus on a single problem at first, but building solutions that can scale. So that was it for my presentation. Thank you, and I can take any questions. Yes. So the question was, did we work on one-off migrations?
Because for one-off migrations, you also need to cut over them, right? If you work on that, how did you approach this? How did you minimize downtime?
Yes. So the question was whether we worked on one-off migrations and how we minimized downtime. So yes, the problem which I mentioned earlier of breaking up some of our monolithic databases into smaller tenant ones, there we did a lot of one-off migrations. And we had we started with the same approach of, it was another platform team which was working on this. So we started with runbooks, and then we built automation to kind of make those migrations. And generally, we did not use the Debezium approach for that. We used the direct Postgres publisher subscriber native logical replication for it. And then we had a set of steps, and we worked with multiple user teams to kind of do the read cutover and then the write cutover. So it was a sequence of steps, and it took a lot of time. But yeah, it is something that we worked on. Right. The question was how were our teams managing transformations on the sync side, right? So yeah, so good question. So for those of you that don't know, Debezium and all the sync connectors, Kafka Connect offers single message transformations to transform each row of data. And we mostly used, wherever possible, the open source single message transformations for Debezium and the sync. But there were many cases where we kind of built our own transformations, because all of the repositories and the code in the Debezium, we have our own fork of it, and we do work on features and message transformations there. So that was the approach which we took. So first, see if it's already available. If not, build our own thing. Yeah, the question was, did we use incremental snapshots? So early on, we did not use incremental snapshot. So wherever it was needed, we just had the snapshot mode as initial or always. But right now, we are looking and implementing the incremental snapshot features because more and more product teams are asking for these one-off snapshots that they want in their target systems. So we are making it like a platform level feature, the initial, the incremental snapshots. So the question was, how do we ensure that the pipeline is reliable if there's any crashes? So there are, of course, there's multiple components there. And going back to the Debezium logical replication here, right? So there are multiple failure modes here, right? So there's the Debezium part and the Kafka part and the sync part. So if a Debezium part fails, then we have the write-ahead logs won't be incremented. So we have those changes which we can then pull, whatever changes have not been applied. So that's how we take care of that. And for the sync connectors, one, we have a lot of these multiple consumers within a consumer group. And if any of those fails, or if a record doesn't make it, then either we kind of crash loop back off and we kind of fail, or we add that message if it cannot be processed into a dead letter queue. So yeah, it's pretty reliable till now. So there's yeah, from my understanding, it processes the data first and then sends acknowledgements back. And Debezium in the documentation have documented that it's at least once delivery. So Debezium takes care of delivery to the Kafka at least once. But there are scenarios where Debezium kind of crashes, and the vol increase is so much on some of our monolithic databases that we have to fix the problem. And if we cannot get Debezium back up again, then we'll have to take measures like dropping the replication slot, which is quite impactful. And those are quite rare. And the way we handle those scenarios is that we just take a snapshot or an incremental snapshot and just get data flowing again. We also have Kafka log compaction enabled on some of our for some of our use cases, and that actually gives you kind of the source of truth in Kafka whenever it's required. So you can just replay all of the Kafka messages and get the true state of the system from there. But there are some other trade-offs like storage there. But yeah, Debezium does say that it's at least once delivery. All right, thank you, everyone.